is a PhD student of mine. His background is the background of a mathematician, but now he is PhD in theoretical and applied mechanics. His talk will be followed by a master student of mine in physics, because I had the honor of teaching only 1 year analytical mechanics for theoretical physics in Naples. Then they decided I'm not good enough, so they throw me back to engineering school. Okay. So I suggest to gather the two talks, which are two sides of the same coin. So we speed up, and then you raise questions. I hope that you will be interested for this. Okay, please.
Okay, good afternoon to everyone. This is a rather novel approach for challenging a classical problem, modeling deformable bodies. And the fact that this is a novel approach is also visible from the fact that we were uncertain about the title, because up to the last moment we were thinking about swarm robots or generalized cellular automata, and I will explain you why. So basically my talk will be just a medium between the basic idea which came from Professor Della and the really interesting stuff which will be shown by Antonio afterwards. So what is a swarm robot? This is the classical definition by Gazzi and Passino. A set of agents possessing independent individual dynamics but exhibiting intimately coupled behaviors and collectively performing some task. So the first input for studying this kind of models came from the desire to describe the behavior of collective animals like bees, wasps, and so on. But they found many application fields. In general, you can look at that. In general, they are very good when one deals with the system performing decentralized and cooperative coordination. The task they are called for, they are supposed to perform, can be the modeling of some specific cases of deformable bodies or even other mechanical systems. For our aims, we started, at least for the moment, trying to model solid deformable bodies. This implies that the concept of neighbors, which is crucial in swarm robotic modeling, has to be Lagrangian. What is my neighbor for an element depends on the reference configuration and is preserved during the time evolution. We wanted a purely geometrical model, so the state of every element is given simply by its position. This can be reached, of course. We wanted low computational cost and flexibility in the choice of possible applied external actions. So in this way, we did not fall exactly inside any category, because swarm robots are usually based on Eulerian concept of neighborhood. Whilst cellular automata, their elements usually have a finite number of states, typically 2, and a simple and local interaction law, which I will describe, is not what is usual in molecular dynamics, in which usually you use equation of motion.
Excuse me, this is just a technical question.
Yes.
What is the exact meaning of Lagrangian neighbor?
I will explain in a moment. Anyway, it means just that what is neighbor to a certain given element is a concept which is preserved during the time evolution of the system. So, as you will see, it's a distance-based concept, but you have to take into account the Lagrangian distance in the reference configuration, not the actual distance at a given time.
That's the texture that you have in the initial configuration.
Yes, because we want to mimic molecular relations between particles, basically, having in mind solid bodies. So our assumptions: locality, This entails, or rather it's realized by us, asking that the elements of the swarm move towards the centroid of their first or second neighbors. I will explain in a moment what does it mean. No directionality, so the interaction will propagate through frames centered in the leaders, and no edge effects. This will be clear with the following graphical representation. This is a reference configuration for a swarm. The elements occupy the nodes of a lattice, square lattice. Let's say the center element is the leader, to which we impose a given motion, any motion we want. Then we have a first frame of neighbors in red and a second frame of second neighbors, let's say in blue, and we can go on, third, fourth, and nth neighbors. You say the distance which we refer is the Chebyshev distance on the lattice, and in red it is highlighted the fictitious boundary. What does fictitious boundary mean? Since in the time evolution every element moves in any time step in the centroid of its first neighbors or combined first and second neighbors, in numerical simulation you will see, there will be spontaneous collapsing if no special measure is taken for the edge element, for the boundary element. The way for the moment we adopted is very simple, to choose a fictitious boundary which is at a fixed distance with boundary elements and translate rigidly, with their closest true elements, boundary element. So this is just recalling some basic definitions. What is a centroid? What is Chebyshev distance? How does it evolve? We consider a discrete time evolution between two actual configurations for time steps, let's say k and k plus 1, we have virtual configurations. And what does it mean? Here is described accurately the meaning of a generical virtual configuration. Informally speaking, it means that in every virtual configuration, in the virtual configuration M, let's say, the frame of mth neighbors moves, and each element of it moves in the centroid that its own first or second neighbors had in the previous virtual configuration. Why this? Because otherwise the way in which the interaction propagates will depend on the order by which you select the elements along the frame. Instead, we want no directionality. So, about the energy, we still not have explicitly the energy of the system, but some informal but reasonable, in my view, considerations. The centroid minimizes the squared sum of the distances from a given set of points. This is an elementary geometrical property. So it is natural to think that a suitable energy will depend on squared distances for this system. And a simple remark is that having this in mind and choosing the step of the lattice as the characteristic length for finite differences, it will be easy to express the energy depending on first order finite differences or first finite gradient. While if second neighbors are taken into account, so that the centroid is computed taking into account first and second neighbors. By the way, you can weight them as you want. For the moment, we use uniform weights. This cannot be done. I mean, the energy cannot be expressed as a function depending only on first finite differences. Playing with the definition of forward and backward second order finite differences, you can express it in that way depending on first and second finite gradients. So, about the homogenized limit of a given system, in particular about the
is accepted?
I was in doubt, so I preferred an understatement. It was accepted. So there were two rigorous results about obtaining a second gradient model from homogenizing a particular system. The first one, from Carcatera dell'Isola Esposito Pulvirenti, it contains a general result for 1D case. The second, by Alibert and myself, about a particular pantographic structure of flexural beams. None of this, neither of this, can be automatically applied to our case. We would like very much a general theorem from which will follow as a simple corollary our case, but we don't have it yet. So I will show now just a few cases of numerical simulation just to show what is our toy, but the real appealing stuff will be shown by Antonio. I hope this will work. We select the vertex element in red as the leader, impose to it a motion which is uniform, and this is the behavior we get, very basic. You can see that in the initial part of the time evolution there is only deformation. Then from a certain point on, overall translation begins, and moreover the shape keeps more or less unchanged going ahead. This movie is very short, but you already can see that an asymptotic convergence toward a certain shape is visible. In the second case, we do the same with second neighbor interaction, while in the first case we only had first neighbor interaction. In this case, the qualitatively behavior is the same, but the shape is much more compact, and the effect of perturbing the leader is less sharp, let's say. We compare this with the ordinary COMSOL simulations for first gradient and second gradient 2D continua. This is well known, of course. You can see a certain elongation, applying a displacement, a prescribed displacement in a region around the bottom right vertex.
The side effect related to the...
Yes, I will show this later. No, this is the fine mesh, but it is extremely fine. Then, assuming this standard model by Mindlin for constitutive model for second gradient, isotropic second gradient, we have this behavior applying the same displacement. You can see that the elongation is less pronounced, and the effects of imposing that motion is less localized. And this resembles very much what we got in the previous two cases. Okay, I want to show them again. What happens pushing inside the vertex? This is the first neighbor interaction. You can see that the leader penetrates deeply into the swarm before overall translation begins. With second neighbor interaction, you see that overall translation begins well before the leader can enter inside the swarm. Zooming at the bottom right vertex in first gradient and second gradient, you can see a qualitative behavior. I mean the loss of convexity around the vertex in first gradient case and not in second gradient case. This is exactly recovered in our letting evolve our swarm. This is another very simple case. We imposed a uniform motion to the leader and then stopped it and let the system evolve. We obtain some kind of combined extra friction effect, and in the end the system reaches its original configuration, original shape. This is the case in which the leader, to the leader, a uniform acceleration is imposed. And you can see that, unlike the previous cases, there is no asymptotic convergence to a certain shape. Instead, the elongation keeps, the system keeps elongating, and the angle, this angle I mean, keeps decreasing. And I could cheat here and say that there is some Poisson effect here, because it would be easy to cheat, but actually this is a problem for the moment. We can come back to this later if you want. This is another simple case. We select 6 elements as leaders and pull them. This is the first neighbor interaction. And this is the second neighbor interaction. In this case, remember that the motion of the leaders is imposed, so you have that the leaders are detached more or less from the swarm, while the swarm is more compact than in the previous case. So, let us try to make a rough estimate of the computational advantages, if any, of this toy. This is the mesh we used for our continuous simulation, you saw. It's very fine, and it's the shape of the mesh elements is adapted to the particular case of imposed displacement around this vertex. If we choose a coarser mesh, we get this result. I don't know if I can. Yes, I can. You can see that the result here is not perfect in terms of symmetry, and moreover, you obtain dependence on, okay, I made something very wrong. Sorry for a minute. I shouldn't have done that, because I knew some problem with the horizon. Okay, this is typical from myself. Outside control. Okay, just to say, I was about to, maybe I can roll in this way. If we select a mesh in which the number of mesh elements is comparable with the number of elements in the swarm we consider it, we can see a very bad convergence to something which is not what we would expect in this case. So for the next future, what we will search for? First of all, a Lagrangian formulation for the evolution of this swarm, which is simple in a way, but not so simple, because all this stuff with virtual configurations and fictitious boundary together make the finding of a suitable Lagrangian formulation not so easy to achieve, for the moment at least. Then theoretical results, typical of swarm robotic system theory, starting by aggregation properties. That means the property of being confined in some regions, being confinable in some circumference, let's say, along all the time evolution. And by the way, for selecting one leader with uniform velocity, we already have results for 1D case, but even for this simple question, a result for a 2D case is not available still. And we want to enrich the model to account for many different materials and effects, because you saw this is just a model case. We didn't introduce any constitutive parameter. Already in the presentation by Antonio, you will see that something more can be done with these simple ingredients, let's say. So for the moment I've finished. I leave to Antonio.
We have stayed 5 minutes, so go ahead.
Thank you.
I wonder whether it's not some molecular dynamics without inertia and either a interaction force based on nearest neighbors or
Okay, my answer is yes. My answer is that it can be. We don't know, but the computational force is much less than any molecular dynamics model I have seen. I don't know. Can be that everything can be reformulated with molecular dynamics without taking explicitly into account inertia, but you saw some inertia effect. For example, okay, it will be longer too, but when you have the simulation with the stop motion, or no, better than that, when you have plastic deformation after fracture, you can see that the system keeps overall translation after the fracture, which resembles some inertia effect. So, I don't know, this is my answer.
If you have elastic equation, you just discretize them, central differences sign. Would you get
yes, you don't recover the virtual configurations and the fictitious boundary effects, which taken together can provide this rich set of behaviors. But I don't
not obtain an initial effect molecular dynamics.
you can obtain inertial effect in molecular dynamics. I didn't intend that.
Maybe it should be stressed that the algorithm is forecasting the construction of the configuration of time t plus delta t via many intermediate configurations having
Which are not seeable, not visible.
each of them has an intrinsic time of propagation. So in this way you introduce plastic deformation, friction, inertia. So all this has to be understood. I agree with you, and maybe we will fall inside a particular case of molecular dynamics. But this started as a swarm.
So how, let's say this is only kinematics. How about forces? How about the stresses?
No, this is a cellular automaton. I give you the algorithm.
He proscribed forces for us.
Yeah, but anyway, it seems that you are able to obtain some dissipated energy.
When you observe, I call this dissipated energy. When you observe plastic deformation after a fracture, you can think that once you have a Lagrangian formulation, you will recover inside that some dissipation energy.
I know you are shocked. I want to say that if you have the philosophy of a group, minority group of theoretical physicists, is the following. You write the equations, you write balance of this, balance of that, stress, minimize. At the end, what you do, you look for an algorithm.
But that's not what I'm saying. What I'm saying is you have an algorithm and you can write an algorithm based on molecular dynamics with simple interaction, and if you write down the equations, I think they're the same. And you can move philosophy whether this has deeper meanings, but I think it's likely that you'll find the same.
I think it's a case of more or less giving different names to the same things, maybe. Yes, but I say
So my
typically.
suggestion is to investigate whether such analogies are present.
Of course, a set of analogies have to be investigated. This is a very young topic.
No, but what I want to say, in molecular analysis, dynamics, you write ordinary differential equations, n of them, one, coupling everything.
Yeah, but you discretize them
Yeah, in time.
in time.
But you have already a finite number of Lagrangian parameters, and you write,
It's the same.
yeah, but you write an ordinary system of ordinary differential equations.
But you throw out inertia, I think. So you don't have time.
No, you have time. You have time. What is astonishing, which could be a stupid thing, I don't know, but what is astonishing is that you get inertia, you pull it, and it keeps moving with a given speed. And
It doesn't
I mean, Galileo principle of inertia is the following. You leave something with a given velocity, it keeps going.
Yeah, but can you add body forces? What I would call body
No, you won't body forces. You should ask me, can you interact with this without an algorithm? And I can say that up to now we move leaders. So we move kinematics of some parts. Here forces are not considered enough. And I know this was meant for shocking.
I think if you can say there is no force, but if you interpret in terms of plastic deformation, in the end you put everything at the same time. I mean, either you say there is force, there is energy, and there is plastic deformation, or you say there is moving nose, and that's it. But you cannot say there is no force, but that there is plastic deformation.
But you play with three parameters always. You play with three parameters and you get plasticity, elasticity, friction. So it could be simply a quick way for solving molecular dynamics equation.
It would not be trivial.
Yeah. Okay, so we can discuss about this